Maybe wait for another minute. I have to talk a bit more, I guess. Aaron did his PhD under the supervision of Christine at Columbia, and is right now an assistant professor, still very long, hopefully, at Rutgers University.
Is the position or location going to change?
It's hard to hear me.
The position.
Sorry, I should have used the mic. But Aaron is.
And the recording can't hear you.
You're being promoted. That's true.
Oh yeah. Whenever a question is asked, could you just repeat the question, because otherwise the people on the live stream can't hear it.
I will try to remember to do that. Feel free to remind me.
Yeah, that was hard to remember.
Okay, I'll just have to talk quietly because.
You don't have to talk quietly. And if when people turn and face the slides, and then you can't hear them as well.
But the microphone fixes that.
No. The microphone is very directional. I've noticed that. People turn and look at the slides, and then you can't hear them because you're away from the microphone. Because you're away from the microphone. No one tells the speakers that. No,
Full body.
Yeah, you can't hear the spell on the audio.
I think you're ready. Okay, thank you.
Great. I'll get started. Hi, everyone. Good morning. So this is going to be a talk. Basically, it's a combination of two different results on two different problems. And the unifying technique is, the unifying theme is one technique that we call congestion balancing. And the technique is really what I want to highlight. Okay, so the first part is about matching. So we've seen this problem many times already in this week. So in this particular setting, we're going to assume a bipartite graph. And the adversary just deletes one edge at a time. So say the graph is unweighted, you could make this work for weighted graphs. And the goal is to maintain a 1 minus epsilon approximate matching. So note that maintaining an exact matching is hard, so you really need this 1 minus epsilon approximation. So what we show is to do this very efficiently in polylog update time. And we later extend this to non-bipartite graphs as well. So I'm just going to very quickly talk about the background. I'm not going to talk about all of the background on matching. I think like David and Sohail have already done a lot of that. But just the direct contrast to our work is an incremental result, similar, even better, constant update time, was known before. But the fully dynamic case is very hard. If you want like a 1 minus epsilon approximation, you need something like root update time, or you can do a tiny bit better if you only care about the size of the matching. So basically what we're able to show is like, okay, both decremental and incremental are easy, and it seems to only be their combination that's hard. Okay, so now let's talk about how we get this. And again, the main thing I want to highlight is the technique. Also, this result is very simple. This is like 5 self-contained pages in a paper. So I'm basically going to go through the whole thing, and you should stop me if something isn't making sense, because if it's not making sense, it's not because I'm sweeping something complex under the rug, it's just because I'm not explaining it well. So please feel free to stop. Okay, yes, so for this part, as I said, this is 2 talks, and it's literally 2 talks. I'm going to switch it here. You will note that Thachapal is orange and not me, and that's because I kept that to highlight that this is mostly his slides. Some minor changes, but these slides are mostly due to him from a previous talk.
Pictures a little less broken.
I don't know how to. Got it.
Okay.
Sebastian, the internal
The inside one.
Inside, yeah.
All right. So again, this is the problem. We want to maintain a bipartite matching in a decremental setting. And in particular, to solve this problem, it's enough to solve the following slightly simpler problem, which is that basically in linear time, you're told you have some matching of size mu, that's your max matching. So, and your goal is just to keep track of a matching of size approximately mu, or detect that the maximum matching size has fallen significantly. So when the maximum matching size falls significantly, you don't have to compute a new matching, you just say, okay, I terminate, the maximum matching size has fallen. And it's pretty clear if you can solve the subroutine, you can solve the whole problem. You just, whenever the maximum matching size falls, you go again. So this crucially uses the fact that the update sequence is decremental, so the matching size is only falling. And this sort of new phase can only happen like log n times. Okay, so that's going to be our problem from now on. We start with a maximum matching size mu, and we want to maintain a large matching size mu, or say there's no large matching anymore.
Are we maintaining the matching or just the size?
Matching. We are maintaining the matching.
Question.
The question is, thank you. Are we maintaining the matching or just the size of the matching? We're maintaining the matching explicitly. Okay, so let's try some things that don't work, but that are going to lead us to the final solution. So the first thing you want to try is, let's just be lazy. So the nice thing about a matching is that it's quite stable. Right? If you delete a single edge, that can only change the matching value by 1. So our algorithm is we're going to compute a matching, and then we're just going to wait for like epsilon times the size of the matching deletions. We just do nothing because the matching cannot change that much. After that many deletions, maybe our matching isn't good anymore, so we recompute. That's the whole lazy algorithm. And it's clear this is always a good approximation because matching is robust in this way. Okay, the problem with this is that it's too slow. You're going to have to recompute too many times. So let's see that in more detail. So let's say the original graph is actually just a complete graph. And the adversary is always going to use the same strategy, which is whatever matching you pick, they're just going to delete the edges of that matching. So you start with a complete graph and some matching. The adversary is going to delete the edges of your matching. Now you have an almost complete graph. So you pick another matching. The adversary is going to delete those edges. Now you have something that's still pretty close to a complete graph. And this can just keep going. And the adversary can clearly end up causing you to recompute a new matching n times. But recomputing a new matching costs m. So you have mn total update time, whereas we would like m total update time. Okay, so this lazy approach doesn't work. And let's think about why it doesn't work. Basically, the issue is this, is that your graph has n squared edges, but the matching that you care about has n edges. And so by computing an integral matching, you're essentially putting all of the importance. You have n squared edges, but you're putting all of the importance on only n edges. And that's going to give the adversary a lot of power because they can delete the edges that have importance. So basically, you're allowing some edges to be much more congested with importance than other edges. So in order to fix this, we want our edges to be less congested. We don't want to place too much importance on any one edge. And for this, we need fractional matching. And the nice thing about using fractional matching is that because of the talk that David gave, if you can solve fractional matching, you immediately get integral matching. You don't need to do anything else. So our goal now is just to maintain a fractional matching. Okay. So, and as I said, the idea now is going to be that we're going to try to assign small fractional value to every edge so that there isn't a large impact from that edge being deleted. So in the complete graph, for example, we're going to use the lazy approach again, but our initial matching is going to just be to put value 1 over n on all the edges. And so now note that the adversary needs to delete like epsilon n value to ruin your matching. But that means they have to delete epsilon n squared edges. So they basically have to delete the whole graph just to ruin your one matching. After they delete epsilon n squared edges, okay, you go again, you compute a different one, but now you only have to do this like 1 over epsilon times squared. So fractional matching, way better than integral matching. Of course, the problem is, yes, in this example, you got to put a small value on every edge. That might not always be possible. Consider this graph where you basically have something that looks like a clique up here, but then just a few individual matching edges. You have to put value 1 on these edges in any maximum matching. These edges have to be important. So what we're going to do is basically try to capture a way to say that, okay, some edges are critical, but we're going to show that only a small number of edges are critical. So we're going to find a way to determine which edges are critical and which ones are not. And of course, criticality is like you're not just either critical or not critical. There's a whole spectrum of how weak. So we're going to capture this criticality with a notion of a capacity. So what we're going to do is we're going to put a capacity kappa on every edge. And we're basically saying that your matching is not allowed to put more than value kappa on that edge. And so as a subroutine, you can solve a problem where basically, let's say I give you a graph and I give you capacities. I say every edge is allowed to have at most kappa value, and I want you to find a fractional matching. then this is just a static problem, and this is easy to solve using standard matching techniques. So basically what you can do is you can either find a matching that obeys these capacities, or you can find a cut that says like, okay, on these edges, the capacities are too small, and so it's impossible for me to find a large matching. I'm sorry, I forgot to silence my phone. Okay, so the way you do this is you could just convert to a flow problem, and then you could run like blocking flows, or you can just solve it directly as a matching problem. So the point is you just check, is the max flow mu with these capacities? If not, there must be a cut. You can also formulate this cut directly as a matching thing, but I think it's easier to think of as a flow cut. Okay, so we're just going to assume that we can solve this subroutine in linear time. We can only solve an approximate version of it in linear time, but let's say you can just solve the exact version. It's not going to. Okay, so here's the idea of the algorithm. Again, we want to make the capacities small because we don't want to put a lot of value on every edge. So we start by just giving every edge really tiny capacity. This is laughably tiny. There's no way you can find a matching with these capacities. They're too small. Right? Even if you put value 1 over n squared on every single edge, that would still be a very small matching. So the capacities start too small. And now what you do is you basically ask, or sorry, okay, the first thing you do is you just check that the graph has a large matching. Right? If the matching size initially, this is without capacities, is less than mu, then you terminate. Right? That was our claim. You try to either find a matching with size mu or terminate. So if the matching is small, you terminate. Now, if the matching is big, then as we saw before, you don't want to just pick an arbitrary integral matching. That's not robust. So instead, what you're going to try to do is you're going to try to find a matching with these capacities. So if you find a matching with these capacities, great. That's going to be the matching you're going to use. That's kind of the robust matching. But you probably won't find a matching with these capacities. Initially, you definitely won't. And so initially, this matching or cut thing is going to say, no, these capacities are too small, and it's going to give you a cut. But that cut is giving you information. That cut is basically telling you these edges are too small. Because basically, you know the graph has a matching if the capacities are all 1. That's this first step. So if the second step is returning a cut, what that means is we know a matching exists, but it doesn't exist with your particular capacities. So that must mean that there are some edges whose capacity is too small. And the capacity tells you what those edges are. So you're going to say, OK, these edges, I'm going to double them. And this has to terminate eventually, because once your capacities all reach 1, you know that there exists a large matching. So this is kind of just giving you a targeted way to find the problematic capacities that are too small and raise them. So it's basically giving you a way to detect the critical edges in the kind of simplest, greediest algorithm, where you just, the cut tells you which ones are currently bad, and you double them. And you might double many times. OK, so this is just a picture. If you find your cut, one thing I want to highlight here is if you find your cut, some of the edges crossing the cut might already have value 1. You don't double those. There's no reason to ever have capacity more than 1, because in matching, the vertices have capacity 1. So edge capacity more than 1 doesn't help. But you also cross a bunch of these red edges, and you double their capacities. OK. So after you do all this, you keep doubling. Eventually, you get a matching that does satisfy your capacities and has a large matching and is large. OK, and that's it. Now you do the lazy algorithm. Now you found this special kind of matching, and now you just wait for a long time. Yeah?
Very basic question. Just in the static setting, the
Yeah.
final fractional matching you will get.
Yeah.
Is it the case that for every edge, the fractional weight will be within a constant factor of the final capacity?
What do you mean by the final capacity? Oh, as in, I see. So basically, you get a bunch of capacities,
Yeah.
and then you compute a matching, but it has a fractional weight, which is supposed to be less than capacity.
Yes.
And you're saying, is it like tight with the capacity? No, I don't think that's the case. I mean, we haven't done that, but this is not so refined an algorithm. As in, I think, for example, this will always detect the critical edges. Like if an edge is critical, then this will always give it sufficiently high capacity. But there could be edges that get high capacity even though they don't really need high capacity. That could happen with this algorithm.
Just a quick follow-up question. I just find it slightly counterintuitive, because you are doubling the capacity only when it is telling you that you need to double the capacity. So then you doubled it, and then eventually it turned out to be very slack with respect.
Well, okay, so again, I'm only 90% sure of what I'm saying. We didn't investigate the particular question. But I think when we tried to analyze this, though, the problem is that, like, you found the whole cut. So it's not, I don't think it's the case that every single edge on the cut is like, you might only have to increase some of the edges on the cut, not all of them. It's basically the problem. And so you might some edge might keep participating in a problematic cut without itself really being the problematic edge. Yeah.
Isn't it also the case that when you're increasing just to a certain level, but you didn't know that some of the edges could go much higher later?
Yeah, so some of the other edges will go higher later, and then you don't really need to go higher. Exactly. Yeah, exactly. Yeah. So I think there's, it's only the capacity is only an upper bound. But we'll show the total capacity is small in the end. So it's like, it's still pretty close, but not on like an edge by edge basis, just in an aggregate basis. Okay, so we do all of this just to compute a specific static matching, fractional matching that we claim is robust. And so now we handle deletions in the lazy way, where basically now we have to wait until epsilon mu total capacity is deleted, right? Mu is the size of our original matching. We can wait for up to epsilon mu capacity deletion. Once this is deleted, we just start a new phase. So clearly the matching is always large because we only wait for this much. And what does a new phase mean? Well, it just means that after this amount of capacity was deleted, we now again check, does the graph still have a large matching objectively with all capacities 1? If yes, then if no, then we terminate. If it does still have a large matching, then you start again looking for a matching with this current capacity and doubling it if it's too small. The only key thing is that the capacity function kappa, you kind of reuse the previous capacity function. So you have some capacity function, you delete a bunch of edges, so you deleted too much capacity, so you go again, but you stick with the capacity function you have, and you ask, okay, with that capacity function, do I still have a large matching? And the answer might be no, because some things were deleted, and then you start doubling. But the key thing is that the capacities are monotonically increasing across all phases. Okay, that is the whole algorithm. So are there any questions about the algorithm before I do the analysis? So I should note, it is totally possible for the adversary, for this to happen pretty quickly. You might have some edges with capacity 1, and then the adversary can just delete a small number of edges and force you to start a new phase. But basically what we're going to show is that, yes, if the adversary deletes critical edges, that makes you do a lot of work, but there are only few critical edges. Over the entire sequence, there are few critical edges. And so this just can't happen that often, that the adversary deletes your critical edges. Yeah?
Can you just say how you should update mu? I mean, probably.
You never update. So mu is sort of given to you, and you're told you have to either find a matching of size approximately mu or certify that none exist, and then you terminate.
Right.
So basically, in this step, if the maximum matching is less than mu, you just terminate.
But presumably in the new phase, mu gets updated.
No, so this is all just for one value of mu. That was kind of, then like if mu becomes smaller, then you literally restart the whole algorithm. You throw everything away, all the capacities, everything, and you just restart. That's kind of what I had on the first slide, is that like, if once your matching size drops by a lot, that can only happen log n times objectively. So that's just like log n different like wide global iterations. We're just focusing on a single one where we're told mu's fixed throughout this whole thing.
Oh, so terminate just means that you update mu and you reinitialize kappa. Is that correct?
Yeah, terminate means you update mu and you like start the whole thing from the beginning. Yeah, exactly. Yeah. Yeah.
So the total deleted capacity being epsilon mu is not the same as the size of the matching decreasing.
Exactly. So yeah, that's good. So the point is, it's kind of, we saw in the complete graph, the adversary can delete your capacity, but there's still a large matching. The reason, so it's like, that's kind of the bad case. If the adversary actually deletes, when the adversary actually reduces the size of the matching, that's good, because that can't happen very often. The bad case is when the adversary deletes your matching, but there still exists a large matching, so now you have to go spend time recomputing it. Yeah.
And it seems like at least the iterative thing is trying to solve this like problem of minimizing volume while ensuring that every cut has sufficient size.
Mm-hmm.
But the critical thing seems to be that you're starting with this 1/n² uniform point. right? Like in the sense that like the optimal solution to that like volume minimizing problem is just the matching, the optimal matching. But because you're starting with this like uniform solution, you seem to get this entropy type properties.
Right. So okay. So sorry. So are you saying like?
Repeat the question.
Yeah, I can. So I think you're asking like. I'm not sure I fully understand the question. So I will do my best. But basically, like, so there are many optimal matchings, but we find a specific one that, as you say, kind of has like is kind of has high entropy by starting with this uniform distribution. I agree it's crucial to start with the uniform distribution. Absolutely, that is, we need to do that. And the final analysis, although we don't do it this way, seems reminiscent of an entropy analysis. So, but I think kind of the main thing we need to prove is sort of that this, like we're going to show, the thing is this also needs to work in a dynamic sense. So we're going to show not just that like at this stage, like after the first time we do this, we can show the total capacity is relatively small. But then what we also have to show is that even after the adversary deletes edges, and we have to do this again, and the adversary deletes edges and we do this again, the total capacity is going to remain small. And I think that's, yeah, that's kind of where the trick was.
Right.
Yeah.
Just risk connecting to your question. So you can maximize entropy and that works. Is there a connection to this in entropy maximizing? I've not thought about this.
I'm really not sure. That's kind of a question I'm going to ask you. There's going to be a part where I say our analysis a bit ad hoc. I bet there's a more principled way of doing it. So
we did show this. You can maximize entropy and it works.
Wait, sorry. You're saying you did this?
Yes.
Okay, tell me more.
We have a follow-up paper. You can maximize entropy over like fractional matchings, and that has the same deletion property.
Oh, that has the same deletion. Oh, okay. Sorry. Okay. That question has just been answered.
Just to connect to that question,
Good.
I wasn't going to say
Thank you.
anything, but that question, it's too close.
It's too close. No, I'm going to ask the same question. So, okay, thank you. I want to hear more about exactly how you do it after. So he basically just, I think it'll make a little bit more sense in a. I mean, basically what he said is that another way to, I give a way of sort of, I'm trying to compute a particular kind of matching, which is like kind of catches the critical edges while not putting too much weight on the non-critical edges. And we're doing this using this iterative approach. And what Aaron is saying is that you could do this using a different way by just kind of maximizing a certain entropy function instead of using an iterated approach.
Yeah, so just say if you compute like an entropy maximized solution for some notion of that, anything that solves that problem, any solution to that problem has the property you don't recompute too many times.
Okay,
that's. And if we like use the max flow result to solve it, and we give another method to solve it, this is joint work with a few co-authors.
Yeah, I know this paper, but yeah, I somehow did. Yeah, I guess not in detail.
But just because you said entropy, I thought I had to make the comment.
For the video, do you want to?
Yeah, so I mean, the repetition, sorry, is exactly what I told Valerie, is that they show that like instead of using this iterative approach, you can compute something that just like sort of maximizes the entropy, fractional matching that maximizes the entropy function, and that will just give you what you want. So that sounds really nice. That sounds like a cleaner way of doing it than what we do. Okay.
We could debate whether the methods that maximize entropy are cleaner, but I'll take that off.
Right, there are many, yeah. But anyway,
take that off.
For now, we're sticking with this one. Okay, so our goal now is to analyze the running time. And in particular, what we're trying to figure out is how many phases you have. Or rather, no, more specifically, we're trying to figure out how often you call this function matching or cut, because that's where all the work happens. You have to call it, you have to keep doubling capacities. Now maybe after a while a new phase starts, you have to keep calling it again. So the question is, how many times do we call it over all phases? Okay, so this is kind of a high-level slide, but I think I've gone through all this. We put it that we're just trying to balance the congestion, and we're using the capacity to balance the congestion. Okay, so let's do the time analysis. The key step is to argue that this total number of doubling steps that over all phases that we have to double the capacity is only like log n. So let me formalize this a bit. Here's how we're going to do it. So as I said, the capacity is monotonically increasing, and that's really crucial. And so we're going to define this function that's formally monotonically increasing, k all, where basically we want to be monotonically increasing, but edges get deleted. And so to still be monotonically increasing, we're going to define the capacity even for a deleted edge. So when an edge gets deleted, that sort of its capacity is frozen, but it's still contributing to K all. So this way, edge deletions don't decrease capacity. Okay, and now it's clear our capacity function only increases because all we ever do is double capacities. So what can we say about K all? Well, there's the initial capacity, which is very small. And now, every time we do a doubling step, we increase the capacity. But how much do we increase the capacity? Well, we increase it by the size of the cut. But the size of the cut must have been less than mu. Otherwise, it would have been a matching. This was a cut certifying we don't have a matching of size mu. So the cut has size less than mu. So when you double it, you increase the capacity by mu. So every time you double, you increase the capacity by most mu. So the total amount of the capacity increase is the number of doubling steps times mu. So if we accept this key lemma for now, then the total capacity ever is at most mu log n. So let's accept the key lemma and see that this basically finishes the analysis of our algorithm, which is that our total, so we know our total capacity is mu log n. So what is the number of phases? Well, the adversary has to delete epsilon mu in order to cause a new phase. So what that means is that the number of phases is only log n. So what is the total time? Well, basically, every time during a new phase, we have to call matching or cut to figure out, is there matching or is there cut? And also every time we double, we didn't find a matching, so we have to call matching or cut. But both of these are just log n, and the time to find a static matching or cut is just linear, so our running time is like m log n. Okay, so given the key lemma, that's the whole analysis. So if there are no questions, the next step is proving the key lemma. Yeah.
Is there some reason to believe that the dependence on epsilon is tight?
No, I don't think so. And I think you guys improve the dependence on epsilon, right?
We have like log n over epsilon squared recomputations, if I recall right. And then since it's an entropy problem, we can since the problem is like a clearly specified decoupled optimization problem, we can just invoke the max flow result and solve it. So you just solve in almost linear time.
Ah, I see.
So you get log n over epsilon squared is the total m bunch of subpolynomial factors over epsilon squared is the total time.
Is the total time. I see. Whereas we're getting another cubed factor.
Yeah, so it saves 2 epsilons.
It saves 2 epsilons. Okay.
At the cost of the subpolynomial factor.
Right. I'm also not 100. I think this is right, but yeah. But you have to but then you have to. This is for one value of mu. So we add additional epsilons. We don't optimize, but yeah, they get it down better. Okay. So it remains to prove the key lemma. So let's do that. So we want to prove that the total number of doubling steps is like log n. So yeah, I think it's a nice proof. It's not complicated. It does feel a bit ad hoc. And so I had this whole thing of, can we do a better proof? It sounds like that problem has been resolved. So there is a better proof, but you're going to hear the slightly more ad hoc proof.
Oh, I forgot about
that. Okay, so here it is. So what we want to claim is that if you keep doubling capacities and you still can't find a matching with those capacities, that means there just objectively is no large matching left anymore, even with capacity 1, and then you can terminate. But basically, after you double enough times, your capacities are big enough. So if you can't find a matching, it must not exist. So how are we going to argue this? We're going to use a potential function based on min cost matching. So let's have some definitions. So I'm going to set the cost of an edge to be basically log of the capacity times an n squared to keep everything positive. And then just consider the set of all integral matchings. So the potential function is just going to be on integral matching. The potential function doesn't care about capacities. The only reason it cares about capacities is because they influence costs. But the matching themselves are going to be integral. And then the potential is just the minimum cost matching. So again, these matchings are integral. They don't respect capacities, but capacities influence them because low capacity edges are getting lower costs. So essentially, the potential is trying to find a matching that's using low-cost edges, or in other words, it's using low-capacity edges. Okay, that's our potential function. And let's just see some nice properties of this potential function. So, okay, every edge has cost at most log n, because the capacities are at most 1, and so you get log n as the cost. So even any matching you pick just has cost mu log n. Max matching size is mu. So the potential is always at most mu log n. And now we have a standard potential argument. It's upper bounded for this reason. Yeah, so this was saying every matching has capacity, every edge has cost at most log n, so the total cost is mu log n. And note in particular that capacities are less than 1, so that's why every edge has cost at most log n. Okay, so we finish this. We know that we have an upper bound on the potential function. We know that it starts bigger than or equal to 0, because initially our costs are all positive. And it only increases because we only double capacity, so we only increase costs. Okay. So the final step is to say that every time you do a doubling step, you increase the potential by a lot. Clearly, these three things together give us what we need, and you have a few doubling steps. So let's go ahead and do this. So let's prove this step. Okay, so we want to claim that every time you double, the potential increases by a lot. The proof is quite simple, which is just, so let's look at this cut and consider any matching. And I'm going to claim that this matching uses a lot of these red edges. And so when you increase the cost of these red edges, the cost of your matching goes up. So I'm going to prove this for any matching, that for any matching, any maximum matching, its cost must go up as a result of this doubling step. So pick any arbitrary matching. So it's enough to show that this matching intersects a lot with these red edges, because those red edges, when you double them, their cost increases by 1, right? Because cost is log of capacity. So if the matching uses a lot of those red edges, then and you increase all of their costs, then the cost of the matching must increase. So we just need to show that any maximum matching uses a lot of red edges, and this just follows from the definition of cut, which is basically that the red edges are everything that's not the blue edges. So the claim is that just the blue edge is enough would not allow you to have a large matching, because this is by definition a cut, right? We know that all of these blue edges together are at most the capacity of the cut, which is at most this like 1 minus 10 epsilon mu, because your cut is certifying that you don't have a matching of size 1 minus 10 epsilon mu. On the other hand, we know that the matching you're finding has to have size 1 minus epsilon mu. That's how we're looking at specifically matchings with this large size. So we're basically exploiting a slack we have. And so that remaining 9 epsilon mu, that has to come from the red edges. This was a small cut, yeah, a lot of its value has to come from the red edges. And that's it. Those red edges increase in cost, and so your overall potential increases. Okay, that's it. That's the whole analysis. So are there questions about this last part? If the algebra isn't making sense, again, the argument is just that this was a cut. So what it means for it to be a cut is that its total capacity was not very big. So there can't be that many one edges on it. It must be that the reason its capacity wasn't that big is because it's using a bunch of these red edges that have low capacity. And now you're increasing their capacity, so you're increasing the cost by a lot.
This is a typo, right? The bottom line, it should be, you're looking at the ones that aren't in. Oh, well, you're right. No, yes, you're right. It's minus. Never mind.
I think it's A. Yeah.
That's right.
Or M prime intersected the cut. Like the crucial thing should have an intersection somewhere.
This?
The thing that
it's
says
right.
crucial.
No, this is, okay. I think it's correct, but I also don't think it's worth going through.
Fair enough.
Yeah. Okay. I have a whole second thing I'm going to want to cover. We'll see how much time there is for that. Okay. So to summarize, the basic approaches are going to be lazy. We're going to compute a matching and then wait for the adversary to delete things. But the problem is that if you just pick an arbitrary matching, you're kind of condensing all of your importance on a small number of edges, and congestion balancing spreads that importance out. Great. So this was basically a showcase of the technique, relatively simple. And now I want to show how we use the technique inside kind of a larger, more complicated problem. In particular, rather than using it to maintain a matching, we're going to use it to maintain an expander witness. Okay, so that was the end of that part of the talk. How much time do I have left?
25 minutes,
Okay, not so bad.
including questions.
Including questions. Okay, let's see how much we can get through. True, but we'll probably have more. Okay, let's breeze through the problem then that we want to define. Okay, so single source shortest paths. You have a graph, you have a source, you want to maintain distances from the source. So in the static case, this is easy to solve. What about in the dynamic case? So fully dynamic is hard. I'm not going to go through this, but basically you can show fully dynamic is hard. So people turn to the decremental case. And some motivations for decremental are the ones we've gone through many times in the seminar. And one is that we can use this as a subroutine in many static algorithms. Oh, no. Yeah, we can use it as a subroutine in dynamic algorithms, but also in static algorithms. Okay, so what was known about this problem? So let's just take the simplest version. We have an unweighted graph, so each update just deletes an edge. So we start with some graph G, and we end with an empty graph. So basically, the trivial thing is to recompute single source shortest paths from scratch after every deletion. It takes m time to recompute. M deletions, that's m squared total time. There's a classic improvement down to mn. And there's a conditional lower bound showing this is optimal for the exact case. So we turn to the approximate case. What can you do if you allow approximate distances? Okay, so this is the problem. Each update deletes an edge. We want to maintain approximate distances. So this is a problem that there are like many papers on this problem. Like this was the classic dynamic problem for a while. In 2014, it was largely settled. So this is Sebastian, Monica, Danyapan. They showed you can get almost linear total update time. So basically the same amount of time it takes to compute just a single shortest path tree, they can maintain a shortest path tree over the whole sequence of deletions. So this is great. It has one problem though, which is that it only works against a non-adaptive adversary. And yeah.
Sorry, I lost track of something basic. Is this directed or undirected graphs?
Undirected. Okay. Yes, undirected. So if you want an adaptive algorithm, if you want an algorithm that works against an adaptive adversary, this problem becomes much harder. So there was kind of this follow-up work that tried to improve it, but you could see it's very far from almost linear. And so our result is to get almost linear deterministic. So this is a nice data structure now that you can just sort of plug it in anywhere as a black box. It's deterministic, so it will work in any static setting. So this, I think, finally concludes the problem, except for the subpolynomial. Okay, so and one nice thing about this is, again, you can plug it into data structures. And in particular, at the time, we were excited because this got the first approximate min-cost flow algorithm in almost linear time. That result is totally obsolete now. But it's a nice data structure. I think we'll find other uses. So for example, currently it's being used for fast construction of Gomori-Ho trees. So it makes sense to use in a lot of flow type settings. Okay, so what I want to do is not tell you the whole result, but narrow down on one part of the result and talk about that part, because I think it's the most interesting part, and also because we solve it using congestion balancing. So again, this is the problem, but I'm going to quickly change the problem to talk about a very specific key subroutine. So at an extremely high level, if you look at almost all the fast algorithms of this problem, adaptive, non-adaptive, they're all at some level breaking the graph up into a bunch of low diameter balls because evidential log trees works well for low diameter balls. So this is a highly informal claim, but they are all at some level doing just this. So as a static problem, it's easy to cover a graph with low diameter balls. But dynamically, it's kind of hard to cover a graph with low diameter balls. And in particular, even the following really simple thing turns out to be hard, which is, let's say I give you a low diameter ball. I tell you this is low diameter, you verify it. And now I start deleting edges. And all you have to do is just maintain a low diameter core inside that ball. Or say this ball is no longer low diameter. So let's formalize that. So just some basic definitions. In particular, we're going to be using an unweighted graph for this talk. And when I talk about diameter, I mean weak diameter, but it doesn't really matter. So here's the problem that I just tried to formalize. So here, instead of starting with a particular ball of low diameter, I'm going to simplify it even more. Let's just say you start with the whole graph has low diameter initially. So I'm going to draw this on the board. You start with a graph. It has low diameter. Now, you delete some edges. And some small parts of the graph might now be further away. But most of the graph is still low diameter. So in this case, you still have a low diameter core that contains most of your graph, and you just have a small number of vertices that are no longer part of your low diameter core. But eventually, you might delete a lot of edges, and your whole graph will decompose into like 3 parts of size n/3 or something like this, with long paths between them. And this no longer has a low diameter core. This is really fully decomposed. And then you have to say it's decomposed. So basically, your goal is to either maintain this core that still has a low diameter, or say, no, this is decomposed, I'm done. That's going to be the whole problem. So let's write that down here. Oh, that's the wrong clicker. So we start with our initial low diameter graph. We want to maintain a large set K that still has low diameter with some slack. We could allow subpolynomial slack. And we want this to be large. We want it to be like at least half the vertices. And basically, we're going to terminate when there is no large core anymore. And so formally, we're going to terminate when at least 1% of the vertices are scattered. So what I mean by scattered is like basically 1% of your vertices are like this, you're allowed to terminate. So you only have to maintain the core if really almost everybody is still in the core. So formally, a vertex is scattered basically just means that the ball around that vertex is missing a constant fraction of the graph. So that's our goal. This is the problem we want to talk about. So this is all happening under edge deletions. Okay. So why do we care about this problem?
Yeah.
Yes.
Sorry, your definition of low diameter is there exists a vertex.
There exists a vertex for which the ball around it contains at least half, or all vertices?
No, so you're explicitly maintaining the low diameter set K. And what it means for it to be low diameter is just any 2 vertices have low distance. Yeah. So the reason I bring up this problem is because I think that it basically distills a building block that's common to many of the previous algorithms. They don't define a problem like robust core, and they're usually doing something more complicated. So you might not see it this way. But I think in essence, they all have to, in one way or another, implicitly solve this problem, because they're all breaking up the graph into low diameter balls. And at the end of the day, you have to keep track of, is this ball still low diameter? Or do I have to throw it away and recompute because it's decomposed like this? So basically, our result is in 2 parts. First, we show how to solve this problem. Because this distilled problem, the reason it's important is because it's common to all these other algorithms, but it turns out to be really hard in the adaptive setting. And so our main contribution is we show how to solve it. The second thing we do is kind of motivating my claim that this is the essence of a lot of the algorithms, in that we basically show like the existing algorithms use many different complex, sophisticated techniques, which are all necessary. Basically, what we show is that at the end of the day, the hard part specifically about adaptive adversaries is this robust core problem. So we basically say, like, if you just have if you have a black box just for robust core, then you can use all these other techniques that people have developed to transform this robust core algorithm into an algorithm for the general problem. And all of this works just fine adaptively. So basically, you need all of these techniques, but The hard part about additivity is not from any of these techniques. The hard part is just here, just in robust core. And so we kind of managed to single out that one part that's hard for adaptive adversaries, and now our goal is to solve it. Okay, so let's quickly talk about previous attempts to solve this problem. Again, other papers don't do so explicitly, but implicitly they're solving this problem. And so I said that, okay, this problem, robust core, is the hard part for adaptive adversaries. And in particular, it's actually really easy within oblivious adversary. So the algorithm, I'm low on time, so I'll just quickly say it, is basically you pick a random source in your graph, and you maintain a ball around your random source. And that ball, that just is your core. So you have your graph, you pick a random source. Initially, your graph has low diameter, so the ball around the random source is the whole graph. Eventually, that ball might lose some vertices, but you just maintain that random ball. Okay, at some point, your ball might become too small. And so at this point, maybe your random source has become, your ball has become too small because your random source is here, and the graph is decomposed, and in that case, you can terminate. But it's possible that your random source was here, and so the ball around the random source became too small, but there still is a low diameter component. So in that case, you basically have to start from scratch with a new random source. You're not done yet. You still have a core. You just happen to pick the wrong source. And so now you have to go again. And the analysis exploits the fact that this source is random. So basically, if what we can say for sure is that you had to restart because your ball around S wasn't big enough, so S is scattered, but S was picked randomly. So if S is scattered, that means in expectation, half the vertices are scattered. So in expectation, you're allowed to stop. You're allowed to stop when half the vertices are scattered. And with high probability, you can stop after log n of these random sources. So basically, picking a single random source and maintaining a ball around it is efficient using like classic evidential log tree. And you only have to do this a few times because you pick the sources at random. I think Thachapal talked about this in his bootcamp, the sort of power of the random source technique. Is that true? Yeah. Well, anyway, this is somehow the thing about this technique is it works really, there's a really simple solution against a non-adaptive adversary, but it totally fails against an adaptive adversary because the adversary can figure out your source. They can sort of use queries easily to figure out which your source is. And so basically you pick a source and all the adversary is going to do is it's going to delete only the edges around that source. And so your graph still looks basically the same as before. Like you pick a source, and the adversary just deletes the edges just around the source. So the graph is essentially the same as before, but all of your work was for nothing because your source got destroyed, and you have to pick a new source, and you have to keep going. And so in the end, the adversary can basically force you to pick every vertex as a source. So this is very inefficient against an adaptive. So there's this simple trick. So basically what we did is we distilled the problem down to this one part, robust core, that's hard for an adaptive adversary. And that one core part, you can really see the difference. There's this simple trick that works so well against a non-adaptive adversary that completely fails against an adaptive adversary. And I think the simple trick is actually like, it's not just for this problem. I think there are a lot of problems where, dynamic problems, where they use randomness in various ways, but if you really distill it, a lot of the randomness can be made adaptive or gotten rid of. And it all boils down to this trick. I think there are a lot of algorithms where essentially this trick is the reason that it only works against a non-adaptive adversary. Okay, we don't have a black box way to make this trick adaptive, but we can do it for this problem. So that's what we're going to do. Okay, so I'm going to skip this part. Okay, so here's how we solve this problem. How much time do I have, Sebastian?
Now it's 10 minutes.
10 minutes, great. Okay, so here's how we're going to solve robust core. So for this, we're going to use vertex expanders. So let me erase here. I'll just.
It's unweighted graph.
Yeah, this works for weighted, but we're going to assume unweighted for the talk. Everything works for weighted graphs. Okay, so a vertex expander is, so basically if you have a graph and you pick any set L, its expansion n of L is basically just all the vertices that L is adjacent to. So this would be n of L. And we say that a graph is a vertex expander if for every set L, n of L is relatively big compared to L, like within a log factor. So for this talk, I'm only going to talk about vertex expanders for those of you who are used to edge expanders. And the expansion factor, let's just say it's always around 1/log n. So why vertex expanders? Why am I suddenly talking about expanders? Okay, one nice thing about expanders is they always have low diameter. So if you can maintain, you want to maintain this low diameter core, if you can just maintain a core that's a vertex expander, that's going to be your low diameter core. But there's a second reason we want to use vertex expanders, which is that they are robust to edge deletions. And I think this here, it's worth having a contrast. So here is a low diameter graph. That looks like this. You have two cliques connected by a single edge. This graph is low diameter, but it's very not robust to edge deletions, in that if the adversary deletes this one edge, suddenly your whole graph decomposes. An expander, however, cannot have this. So if you have an expander and the adversary deletes a small number of edges, it might be the case that that deletion causes a small part of the expander to stop being expansive, to leave, but it cannot ruin the whole expander. It cannot ruin half the expander. So they're robust. And so I'm going to formalize that with this notion of pruning, which is basically that if you have a graph that's an vertex expander and you start deleting edges, then you can always maintain a large core inside the graph that's still an expander. And you can do that for up to like n/log n edge deletions. So you can process a lot of edge deletions and still have a large expander. By the way, for those of you who like work with this a lot, the reason we can only handle n edges and not m is because it's a vertex expander, not an edge expander. Okay. So this is a nice reason to use vertex expanders, is that if you start with a vertex expander, you kind of keep having one for a long time, and that's going to be good for being lazy. So to see the power of vertex expanders, let's assume that our graph is initially a vertex expander, and then think about how we would solve this problem. So in that case, all we're going to do is we start with a graph that's a vertex expander, and our core is just going to be, we're going to maintain that set X. Pruning is going to tell us that we can always maintain a large expander inside our original expander, even as edges are deleted. So we maintain our large expander X. At some point, X gets too small, and then we have to restart. But the point is that this restart only happens after like n/log n deletions.
What is prune of G?
So prune of G is prune is just a subroutine that maintains a large expander. If you start with an expander, it maintains a large expander inside it, even through deletion. So it's maintaining this. Prune is just returning this set X. Okay, so we have to be a little careful here because, so what do we do when we restart? Well, now that we've deleted edges, the graph might not be a vertex expander anymore. So you can't really use this anymore. But let's even make the stronger assumption that the graph is just always a vertex expander until you have to terminate. So basically, all you have to do is just keep track of, is the graph still a vertex expander, or has it been destroyed and I can terminate? And in this case, you could just you maintain your set X. Eventually, it becomes too small because the pruning algorithm stops working. And so now you basically have to start from scratch. And again, look at the whole graph. If it's not a vertex expander anymore, you can terminate. If it is, you just go again. You again start pruning and maintain a set X. So essentially what this is doing is everywhere where in the non-adaptive case you maintain the ball around the random source, that's no longer going to be robust against an adaptive adversary. So you replace that ball with an expander. Okay, so this is the idealized scenario. If you always have a vertex expander, then you can get an efficient algorithm because you can use pruning, and because pruning is robust to a large number of deletions. So you get to be lazy. Okay, is this actually efficient though? Let's do the analysis. So you start with a vertex expander, and the algorithm is you can use pruning to always maintain a large expander X inside of your vertex expander, and this is robust up to n/log n deletions, and then you have to restart. So to sort of run the pruning algorithm takes linear time, and you have to recompute every n/log n deletions, and this is not looking great. This is good in a sparse graph, but it's bad in dense graphs. Okay, so this is supposed to be the idealized scenario where G is just always a vertex expander, and even this turns out to be kind of annoying. So to solve this, this is a kind of a very standard application, actually, of congestion balancing. This is our original paper of congestion balancing. This is basically the problem we introduced it for, which is that this was a trivial lazy algorithm, which is that you just maintain this expander X, and it's robust to n deletions, and you have to recompute it. And the problem is that how do you do pruning? Basically, the intuition is, I won't go into details, you maintain something called an expander witness, which has like n edges. And that's kind of a witness that you still have a large part, that you still have this large part that's a vertex expander. The problem is that your graph has m edges, but your witness has n edges, and so the adversary can just delete your witness. This is exactly what we saw the problem was with matching. That you have many edges, but your solution has few edges. So if you just use an integral solution, the adversary can easily just delete your solution and force you to recompute over and over again. So instead, we're going to maintain a fractional expander witness. And again, we're going to try to have every edge not be used too much, using the capacity kappa. And now we can show that this is robust. Again, the adversary has to delete n over log n to ruin your witness, but they have to delete n over log n fractional value. And so you can use congestion balancing to ensure that the total fractional value is small. And I'm not going to go into details, but it's really almost exactly the same as the analysis I gave for matching. And except that now the potential function, instead of being min cost matching, is min cost expander witness. But it's very similar. Okay, so let me just, in the last few minutes, say, okay, all of that was to solve the idealized case. So this was kind of this was still from the matching paper. The problem is that this only works on an expander. So you need congestion balancing even in the idealized case when the graph is an expander. But what if the original graph is not an expander? Right. Our input to robust core just guaranteed the initial graph a small diameter, but it might not ever look like an expander. So the first thing you might try is expander decomposition. It's really unclear how to use this efficiently. You can use it to get like some improvements, but expander decomposition, you have to build a whole hierarchy. We could not actually figure out how to make it efficient. Instead, we kind of argue that you don't need expander decomposition. And I only have 2 minutes, so let me just kind of give the highlight, which is that let's look at some graphs and again, try to get the notion of critical vertices, just like we had with matching. So instead of edges, it's going to be vertices. So basically, an edge is critical if deleting that edge can cause you to decompose a lot. So in this graph, this edge is very critical. So in an expander, no edges are critical. That's what it means to be an expander. It's robust. Edge deletions don't do much. In a path graph here, basically all the middle vertices are critical. If you delete any of these vertices, if you delete any of the edges around these vertices, you decompose the graph. In this graph here, the middle edge is critical. The parts right around it are critical, but everything else is non-critical. If you delete the edges around here, you have basically no impact. And so one thing to note is that this graph, everything is critical, but this is a large diameter graph. This graph, actually very few things are critical. And what we're able to show is that in any low diameter graph, you have very few critical vertices. And the way we compute criticality is by using congestion balancing. So I'm going to skip everything, but basically you define a notion of a capacitated expander. So now you're an expander with respect to capacities. And the main difference is now capacities are bigger than 1. So you're basically saying these vertices, if I kind of count these vertices as n vertices, then if I look at this cut, I have n over 2 vertices on this side. I have only 1 vertex on this side. But if I count this vertex as having multiplicity n, then it's still technically an expander. So we're basically saying, can I increase some of my vertex weights in order for things to be an expander? And what we're able to show is that using congestion balancing, you can figure out what the weights on every vertex should be. And you can figure out that you can prove that in a low diameter graph, most of your vertices will still have low weight, and you only have a few critical vertices. And so then the idea of the algorithm is when the adversary deletes critical vertices, that causes you to do a lot of work, but we can use congestion balancing to argue that you have few critical vertices. Okay, I'm now out of time. So I'll just stop at this slide.
Thank you, Aaron. We have time for a few questions. Maybe I don't have a question, but a comment maybe for everyone who's interested in this robust K core problem that you mentioned. I think, in my opinion, the cleanest way where it appears at exactly that problem with exactly that algorithm. I think that's Chechi Shang, the low diameter low stretch tree paper in Soda a few years ago.
They also are
Yeah,
maintaining an instrument.
exactly this, and with a very nice write.
Cool. Thanks.
So the analysis for the matching looks similar to some parallel algorithm for parallel multiplicative weight update algorithm for max matching. So is there any formal connection? It looks very similar to what you would do if you want to get.
So can you say more about how it's similar?
I mean, typically, if you have a packing problem and you want to find a parallel algorithm, you start with some 1 over n, and you kind of, I mean, here you're using kind of a blocker for the thing rather than, but there are parallel algorithms which do similar things. They double all the values which have low gradient or whatever is the right
So like
direction.
multiplicative
And,
weights.
yeah. So they take log n iterations, and it's very similar. I think the analysis also.
Yeah,
But I just trying to make a connection, not.
I agree it's similar, and that's kind of why I felt like we're probably reinventing the wheel in some sense. Like there's probably like a principled way of doing this in terms of existing techniques and concepts, but it's like different enough that we couldn't figure out how to analyze it using those things. So we had to introduce this new approximation. But I think I wouldn't be surprised if there's a primal dual way of analyzing this.
I mean, in a very approximate sense, multiplicative weights is an entropic regular angle, and that's what the refinement does.
Right. So it sounds like other people have, maybe figured out how to make this more systematic.
More questions, comments? Okay, great. Then let's thank everyone again.